States.
Our only real time constraint is Luciano's talk at 4, so you have 212 minutes.
Yeah, and then we'll just eat that.
So should I start? Today I will speak about vortex motion and that was Einstein compensation. This is part of my thesis and part of an article published in Journal of Low Temperature Physics last year together with Professor Carlo and by me. I'm not expert in neutron stars, but I hope that I can give some suggestions. And because I am the last, I suggest that if you have some question, please ask me after finishing the presentation. Okay. I will speak about the Grossi-Tyrski equation, motions without and with dissipation for single vertex, vertex and vertex pair, or randomly put vertex pair. Connect with them, I will speak about trajectories, radius of trajectories, frequencies, translation speed, energies, mini turbulence system, decay rate of the total number of vertices, and I will finish with some connection between dissipation and friction coefficient alpha and alpha prime. So, this is the Grossi-Tyrski equation. We perform numerical simulation of vertex motion in trapped and confined Bose-Einstein condensation by solving numerically the 2 and 3D, here in that case the 2-dimensional Grossi-Tyrski equation. Our equation contains a dissipative term, gamma. If you would like to know more about the microscopic justification of this gamma, please read articles by groups of Pinchwit, Gardiner, Choi, Subotan. Here, psi is the wave function, use the chemical potential. We use harmonic oscillator units for length, time, and energy expressed with this formula. And the trapping potential is a harmonic trap. In our case, omega, the rotation frequency of the trap is 0, so the minus omega L term doesn't exist. And what happened if omega exists? In that case, the vortex comes from the boundary. This epsilon x and epsilon y do the condensate elongate, and on the boundary which has the lowest curvature first became excitate, and from there comes inside the vortex. As we increase the omega, the number of vertices increases as well. So in our case, omega is 0, the thread doesn't rotate. That means that we imprint vertices, and how we imprint? We use the Thomas-Fermi approximation for initial condition psi, and we multiply by a function x minus x0 plus minus y0. Plus minus means that if we would like to have vertex or anti-vertex, x0 and y0 is the position of the vertices. That means that in that point, if we put, we have nothing, we have a hole. Here on the first picture, we have the trajectory for one vortex, and on the second picture, we have the trajectory for 2 vertices, for anti-vertex and vertex. I put only one of them, the trajectory for the anti-vertex. We can see the influence of the another vertices, so the shape changed, and close to the center of the condensate, they move parallelly. For gamma equals to 0, this is the purple trajectory. This oscillation happens because when the vertex moves or meet each other, sound waves appear. These sound waves cannot escape the condensate because it's confined, because we have the trap. They come back and reabsorb with the vortices. Another explanation can be that the mass, the central mass of the condensate oscillate, and we have a relatively large vortex core, so that can be another explanation. X0, so where we usually put our vertex, on the line y equal to 0, we put on different x position, we have different initial position, and here the initial position is minus 0.9. For the vertex, anti-vertex, so this is 0.9 plus 0.9, so the initial separation distance is 1.8. And what can we see? As we increase the dissipation, the trajectory became shorter, and the time that the vertex needs to go to the boundary is shorter as well. Here you can see better what happens if we increase the dissipation. The red path is for gamma equal to 0. For small dissipation, the vertex need more time, more cyclical motion to move out to the boundary. On the second plot, we see that as we increase the dissipation, this time became shorter. For a single vortex, the radius of the trajectory can be expressed by the help of x and y component of the trajectory. On the second plot, we see that this trajectory, if we put dissipation, vary as an exponential function. If we increase the dissipation, this exponential function became steeper. For gamma equal to 0, this radius is almost constant. This is the red line. We can calculate the logarithm, for example, for this radius, and we can see that if we put the vertex on different initial position and we choose dissipation, for example, 0.003, this logarithm function increases linearly with time. If gamma is the exponential constant for this exponential function, which is expressed with this formula, this gamma, we was interesting to see how this gamma depends on the dissipation and on the vertex initial position, and we see that this exponential constant increases linearly with the dissipation, and on the close to the center of the condensate and close to the boundary, this increases much quicker, and between this regime, it is almost constant. Here, from the past, we can study the frequency of motion. For example, without dissipation, gamma equal to 0, how this varies with x0, the vertex initial position, close to the center of the condensate is almost constant, and after that increases exponentially. We can do the same things with dissipation. We see that omega behaves similar. We use the first circular path when we have dissipation, we use always the first circular path of the vertex to calculate the frequency, because otherwise it changes with time. Between the frequency and period, this is the relation, and we can see this on this graph as well. Here we have repeated the same things, but now we have vertex and vertex pair. There are difference between this plot and what I showed before. We see that we have a symmetry both for the period and both for the frequency. The explanation can be that when the vertex is close to the center or close to the boundary, if we put the vertex close to the center or close to the boundary, they have the same path. To calculate the frequency for a pair of vertex, we use two formula. The first one is what I use for a single vertex. The second one, the calculation was made with the help of a single vertex, and we put the single vertex. So, for a vertex pair, here is the vertex, and here is the anti-vertex. Here is the center for the path for both. And if we use only one vertex and put on a place where its path goes through these centers, and calculate this single vertex frequency, and use and multiply by square root 2, we obtain value which is close to the another expression's value. We know that when the vertex and anti-vertex is close to the center of the condensate, they move parallelly, and it was interesting to see to calculate this velocity. We know that in superfluid helium, if the condensate is homogeneous and infinite, the velocity can be expressed like this, and this is expressed by the circle. From the y component of the trajectory versus time, we can calculate the velocity for the pair on this way, and we see again that these values are close. These two values from different calculations are close. When gamma is equal to 0, the total energy is conserved, but if we use dissipative environment, the energies decreases, they became smoother, this oscillation disappear, and they became steeper. The same is valid for the kinetic energy, and here the total energy is a sum of the trapping energy, internal energy, kinetic energy, and quantum energy. We was interested to calculate the sound energy and the vortex energy as well. And we know that the kinetic energy has two components, one due to the compressibility, and another which describe the sound energy, and the another without compressibility, the non-compressibility part, which describes the vortex energy. And what was our method to calculate these two energies? Firstly, our Gross-Vitaevsky, when we solve the Gross-Vitaevsky equation, first the program runs in imaginary time to have the proper value for psi and mu, and after that we switch in real time, and we wait when we have a vortex structure. In that case, we calculate the kinetic energy with this So when we have the vertex structure, we save, for example, in that case, we save 4,340 psi's, and with the help of a condor method, we run simultaneously for more than 4,000 programs with this psi as initial condition, and these programs was running only in imaginary time. That means that the system goes to the lowest level, sound wave disappear, and we build up again the kinetic energy, which means that now without the sound energy, and this was the vertex energy, and the difference between the initial kinetic energy and vertex energy give us the sound energy. We see that where the sound energy has maximum, the vertex energy has minimum. That means that there is a strong anti-correlation between them. The correlation coefficient is -844. Here the dissipation was 0, and we used vertex anti-vertex pair with initial separation distance 2.86. So if we have dissipation of, for example, 0.003, the total energy decreases, the kinetic energy decreases, we check all kinds of energy, all the internal energy was increasing, and here we see that there is anti-correlation between the vertex energy and sun energy, but it was interesting that here the correlation coefficient was not a constant, it varies with time, it decreased with decreases with time. For one vertex, for example, our aim in this article that I heard about was to see which kind of connection is between dissipation from our Gross-Bethe escape equation and the friction coefficient alpha and alpha prime introduced by Schwarz 1988 in a vertex filament model where it was involved balance between Magnus and drag force. We had transformed this Schwarz equation for our 2D model, and this is our equation which contains alpha and alpha prime. If we solve this, so the real solution is there. This is in cylindrical coordinate, and R, T, and theta T is the exact solution of the Magnus of the Schwarz equation, but this describe our trajectory as well. So the vertex trajectory was that connect the alpha prime with gamma, because for the trajectory we know which kind of dissipation we used. And with the help of the trajectory, we have information both from the dissipation and both from the friction coefficient. And we observed that alpha, the friction coefficient alpha, increases linearly with gamma. Alpha prime is much less than alpha, therefore is not so easy to calculate. In the most literature they only neglect. Here we observed, I have not the plot, but I can tell that for small gamma it increases, and after became like constant or with different value. We was interested in how this alpha and alpha prime vary with x, and we can see that close to the center of the condensate, where the condensate is much dense. We know from the geometry of the condensate is not homogeneous. Close to the edge, alpha decreases. Alpha prime, which is much less, it's almost constant. choose some plots from a movie. I decided to use plots because I can show better the time, what happens, how interact the vertices and what happens at which time. And here we put randomly 8 pair, that means 16 vertices, 8 pair of vertex anti-vertex. Randomly means that their initial position and their initial direction, so when we choose, we put random number. Due to the fact that the Gross-Pitaevsky equation first ran in imaginary time, and due to the fact that some of the vertices has their initial position outside of the condensate, finally we had only 8 vertices. We used 8, but this was enough for this movie and the study how the total number of vertices vary with time. So what can we see here? We see that a pair of vertex anti-vertex moves across the condensate, and here we can see how if they are too close, they annihilate, and sound waves appears and moves across the condensate, and due to the sound waves, the sound cannot escape the annihilation. Finally, the system became turbulent. And for example, as I told, if we use vertex and random vertex anti-vertex pairs, we can study how these numbers decays with time, and we see that this is exponential. They decays exponentially. Here I put the exponential constant for different dissipation, and our first conclusion was that if the dissipation is small, this decrease needs more time. That, for example, if the dissipation is large, this decay need much smaller time. It happens faster. So our second observation was that this exponential constant decreases linearly with dissipation. And I would like to finish my presentation with some conclusions. Thank you for your attention.
I missed at the beginning is,
Yes.
was the potential a harmonic potential or an inverted harmonic?
Which numbers
At
do
the
you prefer?
At the very beginning,
Very
where you gave slide 3.
3? This, or do you need?
Okay,
this
so
is-
it's a
or maybe
standard harmonic
I can go
oscillator.
back and so here from here.
So my question is, if you put in dissipation, why does the vortex spiral away up to higher, farther away from the origin where the energy is higher?
If we put dissipation, the vertex lose energy. That means, and this is the reason that spiral out. Otherwise, the vertex has the same path with a constant potential, constant energy. But the energy decays, and the vertex will move from where the density is smaller. So, and this our condensate, as I said, is not homogeneous. In the center, the density is much higher. On the close, on the edge, it's smaller.
So it's a property of the background
Yes.
condensate. If
This-
you had a uniform condensate, it'd probably go the other direction, because it costs energy to go up in the harmonic. Well,
I think my suggestion is that if we have dissipation, for example, the total energy is not conserved, it decays. And due to that, the condensate is not homogeneous.
And remind me, alpha and alpha prime are related. They're related to neutral friction coefficients.
Oh, you said.
So I had to. I'm sorry. I said. Someone had to. So in principle, this is almost a way of experimenting with the kind of coefficients and the behavior that we're interested in. In principle.
Yes.
I'm not too hungry to say anything else.
How difficult will it be to put vortices crossing each other?
The cross.
Cross each other in your condensate?
Just a minute. This is only two-dimensional. The cross, I did that when in the beginning of my PhD, I used three-dimensional, and in that case, they meet, and it was, I couldn't see it, but here, it's only one. You can see only that they annihilate. They annihilate each other.
So in that case,
If
there's nothing.
they have different sign. If they have the same sign, they move. So.
So the vortex-anti-vortex pair is more like a vortex loop, no, in the 3D picture.
In
This is
2D,
just a
I
slice of
have
a
an eye.
vortex loop.
And they bend, and
Do we have anti-vortices in the neutron star?
It's been tried the other way.
They could all be anti-vortex.
How do you form a pair of vortex anti-vortex?
pardon?
Experimentally, how do they form a pair of vortex anti-vortex?
But here it's a vortex loop. I think it's a
Yeah.
two-dimensional calculation. So
Yeah.
in reality, this is a vortex loop. So here you just make a slice.
For example, yes.
Three connections.
Yes.
Take two guys, slice them off, form a loop, and then cut through. You've got a 2D system, one up, one down. So that's so. I think the question for us, which we've sort of started to touch on, is this picture that Bennett drew with a 10-kilometer straight line. Is that reality, or is it in fact a number of little loops that are maybe lined up in some sense? And that changes quite a lot. What I'm talking about.
Some turbulence.
Yeah, that's right. And it
Well, it could
changes
be-
the picture.
Could be fairly regular, or it could be tangled, and we call that turbulence.
I mean, the picture we're looking at, where you have this one long line, could be a number of elongated loops with some favored polarization, and then this vortex dynamics quite different when you average it up to the hydro scale.
Or maybe there will be really a vortex-anti-vortex pair if you think about a different superfluid which is counter-rotating in some of the solutions.
No, it's allowed. You could ask if I have a vortex array. Let's talk about long vortices just for simplicity, and I want to decrease the angular momentum of the superfluid. I can do so by adding an anti-vortex, but that always costs more energy than simply removing one of the vortices. So it's
assuming
allowed,
that,
but
you
it's
have
not
an
energetic.
hyperonic superfluid which is counter-rotating respect to a different superfluid. There will be opposite.
Thanks for bringing us back to reality.
I think he's going crazy from hunger.
Are you hallucinating, perhaps?
I think Nicola's just got me insane.
With that statement, perhaps we should break for lunch.
I think we
Let's thank all the speakers again.